Okay. So in our previous class, we had looked into a few concepts, right? With regards to the bias current and how we get this offset nulling done. Can someone just tell me what is this offset nulling? Is it an important uh, concept? Is it an important step in a circuit theory? What's the importance of offset nulling? Yes, can I have a response? Offset nulling. We had studied this concept yesterday, right? So what is this offset nulling? Anyone can unmute and respond. Anish Kumar.
Sir.
Yes. What is offset nulling?
Sir, to make the its effect, to reduce the effect of offset voltage, sir.
Correct. Very good. Thank you. So we have seen previously, right, that there can be a lot of changes in the circuit just because of these input voltages, because of the differences in the base currents, because of the differences in the resistances. So in order to counterattack this, okay, we have a potentiometer resistance. Okay, so this is represented as RP. So I will increase or decrease this resistance based on how it is required. Okay, so ultimately I am nulling, I am nullifying whatever the effects of offset voltages and currents. So moving on with our discussion today, right, we will look into input and output impedances, right? So firstly, let's take up input impedance. So as usual, the data sheet plays a very important role in op-amp, where it gives us a lot of information about the operating temperatures, what is the input resistance, output resistance, okay, the levels of currents that it can generate, how much of gains. So basically, it's talking about the property, the electrical property of a device. Okay, and here we are referring to op-amp. So the resistance, we see that it's about 2 mega ohms. Okay, so how do I get to know that? So I get to know that with the help of this data sheet, and I have put an arrow mark here, okay, so that it becomes easy for you to understand as to how much is the input resistance. So I am getting these values from the data sheet, okay, and we are seeing that we are having an ambient temperature, okay, that is TA, is about 25 degrees centigrades. Remember, in yesterday's lecture we were discussing about the importance of room temperature, right? So when we get down to physics, when we get down to basics, we understand that temperature plays a very important role in the generation of currents, or probably I can, in simple terms, I can say the movement of electrons, right? So heat, light, all these are forms of energy. Okay. The input impedance of any op-amp circuit is dependent on the external components and how they are connected, right? Now, how is this important to us? It's because we understand that whatever is the input impedances, okay, now that is not only because of the circuit, but then it's also because of the other components that are connected. What are the other components? The resistances will be connected. There will be signal generators that are connected. So this signal generators also will have certain amount of input resistance to it, okay, but then it should not be very high than the signal itself. Then what is going to happen? The whole signal is going to get lost. Okay, so these impedances or these resistances should be as minimal as possible. Okay, because there is already an existing impedance, and deliberately putting impedance or resistance to these sources will actually hamper the outputs, which means we are not going to get proper outputs. With all linear applications, some form of negative feedback is provided by externally connected components. Can you give me an example as to what kind of negative feedback that we have used so far? We have connected a negative feedback, right? And how was that connected? With the help of yes, with the help of
Negative feedback.
yes, negative feedback, of course. And it was connected with a wire, or did we use any resistances? So we have seen both the cases, right? Only with the wire and also with the resistance. Remember the voltage divider format, right? So that is what this is talking about, right? This negative feedback is provided by externally connected components. So not only just connecting a wire as a negative feedback, but then we are also using resistances. Remember yesterday we had R2 is in parallel with R3, right? We had two resistances. So that resistance is what we are talking about. Those are the components is what we are talking about. Okay, fine. Now let us concentrate on the circuit here, and you will get to know as to how this input impedance is taken into consideration, right? Fine. So from the negative feedback theory, we know that, see, I want you to concentrate on this plus and minus, okay? Because even though the op-amp looks the same, okay, I'll be showing that in the upcoming slide, wherein this plus will be replaced by minus and minus will be replaced by plus. So that becomes an inverting configuration. Now, since here it is connected to the plus terminal, so it is a non-inverting configuration, right? So this is the signal source, okay, the voltage source, and it is connected to a resistance in series, which is RS, okay, the source resistance that we can say, and it has Ri, input resistance, okay. So this is the feedback that I was talking to you about, which is connected without a resistor. But here you can see you have resistors R1 and R2. So this forms a voltage divider. Okay, so this forms now from the negative feedback theory, the impedance of op-amp input terminal for voltage follower or non-inverting amplifier becomes, so we'll be using the concept of negative feedback, and we'll be using this formula directly. Of course, we are not doing any kind of derivation here. We're just going to make use of the formula. So we see that the feedback, using the feedback, the impedance Zi, input impedance, is equal to Ri into 1 plus, okay, AOL into beta. So what is this AOL? We have seen this AOL is nothing but open loop gain. A is gain, OL is open loop, and beta is your feedback factor. How much or what is the parameter of feedback factor? Most of the times this feedback factor beta is taken as 1. Okay, so I think you have seen this formula in your previous semesters or in your previous classes. Have you seen this? Maybe network analysis, you would have seen it. Yes. Have you come across this formula?
No.
This one you would have seen in network analysis. Okay, so whenever you have a feedback connected, okay, this is going to be your input impedance. So this is an important one, and I want you to remember this formula. Okay, now keep in mind this is not for inverting amplifiers, so that's why I've put here in the bracket. This formula is not for inverting amplifiers, it is for the non-inverting configuration. How do I know if it's inverting or non-inverting configuration? Based on the way that it has been connected here. Okay, so here if you can see, this circuit is actually referring to just the normal feedback, okay, the negative feedback, and then the other one, the one at the below, is the one with the usual resistances, okay, the one which we use for computation of problems. This is referring to the practical circuit. Okay, so can I move on? Please note down this formula. Okay, this is important. We will be using this in problems. Yes, can we move on?
Yes, sir.
Okay, thank you. So ultimately you should understand that this formula is referring to non-inverting configuration or voltage follower configuration. So there are three ways of saying this. Okay, voltage follower and non-inverting configuration. Okay, two ways, right? One is the voltage follower and the non-inverting configuration, or you can also say this is not for inverting amplifier. So in order to confuse you in the examination, the examiner could ask questions, okay, stating that refer to the circuit and write its impedance. Okay, so I might give you one of the circuit and tell you to write the impedances. So you may have to, or probably this might come in your quizzes. Okay, you have your quiz upcoming. So in quiz I might ask you these kind of questions. So you should be selecting the one with this formula. Okay, so this is referring only to input impedance, and that too in which format? Non-inverting format. Okay, now previously it was for the non-inverting configuration. Now we have it for inverting configuration. How do I know it? That's because negative is actually connected to a source. Okay, so whatever input signals that I have, okay, those will be in the inverted format across the output terminal, right? Okay, consider the inverting amplifier as in the figure. We can recall that op-amp inverting input terminal always remains at ground level when the non-inverting terminal is grounded. So we have seen that whatever potential that we are giving to this terminal here, okay, to this terminal here, the inverting terminal will also try to be in the same level, right? So what are we trying to see here? We are trying to see that if in case we are using when it's connected to a ground, okay, so ultimately it is getting drained through the resistor, so this terminal also becomes a ground. Okay, so that is called virtual ground concept. Okay, now the thing that you can recall is, say I have 5 volts here. Okay, so the non-inverting terminal also will try to pull up or try to match up to be 5 volts. Okay, so when this is in ground, this will also try to be in ground state. So that is called virtual ground. Please keep this concept in mind, okay, because this is important. Whenever it is grounded, okay, you can make sure that the other terminal also tries to be in the ground format. Please make note of this. Fine. Now we are looking at the inverting configuration, right? So which means the formula does change. Okay. So this is going to be the formula for the input impedance, but then when it's connected in which format? In inverting format. Your Zi, your input impedance Zi is equal to R1. Now, why is it that we are having only R1 here? That's because both of these terminals are actually at ground potential, right? So this terminal is also in ground potential. This is also in ground potential. So which means whatever input resistances that I have here is only the same thing as good as my R1. Okay, so that's why my input impedance right now is only R1. Okay, because this is also at ground potential and this is also at ground potential. See, you can see a dotted line here. Okay, so a dotted line is saying that it is not actually connected to ground, but then it is as good as being connected to ground because it's a virtual ground concept. Students, I think you are able to understand as to what I am trying to say, right? So whatever voltages are here at one point, okay, let us say the non-inverting side, the inverting terminal also will try to maintain the same level. Since it is connected here to the ground, here also it gets connected to the ground and virtually, it becomes grounded. So this concept is called virtual ground concept. Is that clear? And this virtual ground concept comes into picture, okay, only when we have what kind of configuration? Inverting configuration. Okay, keep in mind inverting configuration when the non-inverting terminal is at ground potential. When the non-inverting terminal is at ground potential, the inverting terminal also becomes grounded. Any doubts here, students? Any doubts? Please feel free to ask. Now I have a question for you. What kind of feedback are we using here? Is it a positive feedback or a negative feedback?
Negative, sir.
Yes, very good. It's a negative feedback. Just that, if you can recall the previous circuit, the plus was at the top and the minus was at the bottom. So it is just that it is flipped off. Okay, but then it's connected to the negative terminal. Part of the output is connected to the negative terminal. So this is a negative feedback format. But then, it becomes easy for us to represent. Okay, if we have it here, just the plus and minus getting inverted. Okay, so can I move on to the next concept?
Yes, sir.
Yeah, okay. So two formulas, one for the inverting configuration, okay. And so for the inverting configuration, we'll be using this. And for the non-inverting configuration, we will be seeing the one which was there previously, right? So we'll be using this, which is nothing but input impedance is equal to, okay, Ri, that is your resistance, okay, input resistance, and 1 plus AOL into beta, okay, 1 plus AOL into beta. Fine. So one for the non-inverting configuration and this is for the inverting configuration. So when a question is asked, okay, you can just draw a circuit, write the formula, and tell as to why it's only dependent on this. So you will have to explain the virtual ground concept, okay, and here you will have to explain this formula, right? Put up this formula and explain what these parameters are, and you can mention that this circuit is without the resistances, which means it's an voltage follower format, and you can see that this is the non-inverting format. Okay, so this is the practical circuit, right? Now let's see a small example. Okay, calculate the minimum input impedance of a 741 op-amp employed as a voltage follower. So which means I am going to look at which circuit. Am I going to look at the first circuit or the second circuit? It's saying voltage follower.
First circuit.
First circuit, right?
Non-inverting.
Okay. Yes. So this is the first one, which is the voltage follower, but in non-inverting format, right? Okay. Fine. So we again refer back to the data sheet and we see that it's about 0.3 mega ohms, the input resistance. Now remember, as I always mention, right, first you should always put the formula, okay? Then one by one you can start filling in the values. So you need to know what is input resistance. Since it's not given in the question, you'll have to refer to the data sheet, and from the data sheet you get to know that your input resistance is about 0.3 mega ohms, right? Then the gain AOL is 50 volts per divided by 1 millivolt per millivolt. So which means 10 raised to minus 3, it goes on top, becomes 10 cube, right? So this becomes 50,000. Okay, so we'll try to fill in these values here, okay? And one of you can just calculate and tell me if these values are right. Okay, so 0.3 comes here. This is actually for input resistance 1 plus, then AOL, I have the value here, okay, and beta as I was mentioning, okay, we take it as the feedback factor as 1. So are we getting the same value? Are we getting about 15,000 mega ohms?
Yes, sir.
Yeah, so which means it is like 15 giga ohms, isn't it? Which is a huge resistance. What do you understand by this? It's a huge resistance. Now, if you can recall, the properties of op-amp, what was the input impedance? How much was the input impedance? How much was the input impedance? If you can just flip across your pages and see, you would have written the input impedance of op-amp. How much was it? Was it finite or infinite or very large input impedance? Yeah, how much was it? Okay, I will take you back and we can have a look at it. The properties of op-amp.
1 mega ohms.
Yes, it is actually very huge, right? Let me show you that. Okay, we had discussed the properties.
1 mega to 10 tera.
Correct,
Oh.
correct. So let me just show you. What is the input impedance? Infinite, right? Infinite, which means huge input impedance. Okay, so this is what we are talking about. So you should keep in mind, okay, all these concepts which we discuss. Okay, it's very much necessary to keep in mind. If not, there's no connection between one point and the other. Okay, so keep noting down of the formulas. Okay, try to make your own notes and try to understand as to what these formulas are referring to. Okay, fine. So with this problem, we try to understand that our input impedance is very huge. Okay, so which means it is following the property of an op-amp. Okay, so I have just put up some more information, some additional information as to what are the takeaways from this problem. Okay, so the impedance of source, signal source, which is RS, is connected at the input of an op-amp circuit. Just look at this RS, the A figure, right? RS. So this is the resistance that we are talking about. This should be very much smaller than the amplifier input impedance to avoid loss of signal. As I mentioned, if this resistance is too high, can I pass the information signal to the circuit? Am I able to pass if the resistance is too high? We have Vs there, right? So this Vs is connected, and let's say this resistance is too high.
Yes, sir.
So if it's too high, will this waveform, whatever that I'm generating, will it pass inside the circuit? Is it possible for this to get inside the op-amp? Not possible, right? Because of the high resistance. So we should make sure that this resistance is minimal, okay, so that this waveforms or the voltages are actually able to get into an op-amp. Okay, so it should be very much smaller than the amplifier input impedance to avoid signal loss across RS. So across RS, there's going to be a loss. Okay, and that loss is nothing but signal loss. So this is not difficult in the case of a circuit like the one investigated in this example. So in this example, we saw, we are having about 15, giga ohms, very huge, very huge. However, okay, there are other circuits in which the input impedance is reduced by the presence of externally connected components. So not only, we are able to, play around with these resistances, but then externally connected, just like how we saw the concept of offset nulling, where we connect a potentiometer and the variable resistance. Through the help of variable resistance, we are able to change the values, right? We are able to nullify the offset values. Okay, so students, any doubts till this concept that we have discussed so far?
No, sir.
Yeah, okay. So ultimately, you should understand what are we understanding. We have a formula for the voltage follower, okay, which means the non-inverting configuration. We have different input impedance, and for the inverting configuration, we have different input impedance, right? And these are very much dependent on how the feedback is given. And the virtual ground concept is important. Okay, how the virtual ground comes into picture. I might ask you a question in your semester exam. So what is virtual ground? So you will have to put the circuit, okay, and explain what is virtual ground. And you can also include your answers with Zi, which is equal to R1. Okay, now we will look at output impedances. Okay, so the impedances which are across the output terminal. So we have seen, the input side. Okay, this side we have seen. Now we are going to see at the output side as to what kind of precautions that we have to take for the circuit to be working better. So we see that, we have about 75 ohms. Okay, 75 ohms is what we are referring to the data sheet. Okay, here you can see that there's about 75 ohms of output resistance. Okay, now as mentioned previously, we had used about 0.3, right, 0.3 mega ohms as input resistance, right, and we had used this in the problem, isn't it? 0.3 mega ohms, right? As in the case of input impedance, the output impedance of op-amp circuit depends on the negative feedback. Okay, so the output very much depends on what kind of feedback that you are giving. Now remember, I had told you with the help of negative feedback, we are trying to stabilize the output, isn't it? Yes or no?
No. Yes, sir.
Yeah. So we were able to have less oscillations, right? We were able to have less oscillations just because of this negative feedback. Okay, so we have the formula now, okay, for the output impedance. Z0 is equal to R0 divided by 1 plus AOL into beta. So what was our input? Our input impedance, we had, this is R0 divided by, right? So this is Ri into, okay, so this is Ri into, and for the output it is R0 divided by, okay, so R0 divided by 1 plus AOL into beta, right? So here R0 is referring to output resistance without negative feedback, and AOL is actually referring to op-amp in open loop gain, and beta is the feedback factor, which we usually take as 1, right? So when output impedance question is asked, okay, you can say that it's in the range of 75 ohms. You can put the formula, you can say what is R0, AOL, and beta, right? So we'll see a small problem here, and we will try to understand. Calculate the typical output impedance of a 741 op-amp connected to a function generator as a voltage follower. Okay, so which means, which circuit are we referring to? The one without resistances or with resistance? So are we referring to this circuit, the first one, or the second one? It says voltage follower configuration.
First ones.
Yeah, so we are referring to the first one. Okay, fine. So we find that from R0, okay, from the data sheet, R0 is about 75 ohms, right? We have seen this here, 75 ohms. See, while calculating problems, we take the typical values, okay, fine. And AOL, okay, the typical value of AOL is about 200 volts per millivolt. So which means the same thing happens, it becomes 200,000. And I try to substitute those values. Someone please calculate and tell me if these values are right. Please take out your calculators and tell me if these values are coming out to be 0.004 ohms.
Correct, sir.
Okay, fine. So so we are looking at very small output impedance, right? It's very small, 0.004 ohms is almost negligible. Okay, op-amp circuit should be much larger than the circuit output impedance. Okay, so which means whatever is the output impedance should be as small as possible. Okay, so any doubts here?
No, sir.
Okay, so now if we again get back to the properties of op-amp, what about the output impedance?
0, sir.
Yeah, zero output impedance. So we can see that with the help of this problem, it is almost negligible, right? 0.004 is almost negligible, it's as good as, so we say that it's as good as zero. So we say that the output impedance is zero, and then the input impedances are infinitely large, so in the range of megohms, gigaohms, and 10 raised to 12, which are in fact two huge resistances, two huge impedances. Okay, fine. So I have included some additional information here, okay, which is needed in order to understand, okay, what is the impact of this problem. Okay, load impedances connected to the output of op-amp circuit should be much larger than the circuit output impedance. So circuit output impedance should be very small, okay, should be very small. So that is what we have seen. Circuit output impedance should be very small to avoid any significant loss of output as a voltage drop across Z0. So why is that we need very small impedance? So that there is no loss across the output. Now, if I have huge resistances across the output, right? So whatever signal is supposed to be taken at the output is all lost because of the resistance. So I cannot have huge resistances at the output side. Here again, this is not difficult with very low output impedances produced by negative feedback. Okay. However, there is another limit to the load that may be connected at the output of an op-amp. This is called output short circuit current. Output short circuit current. So if a question is asked what is meant by output short circuit current, then it means that there is another limit to the load that may be connected at the output of an op-amp. So at the output you have a resistance, right? So this is the output short circuit current. So generally when we talk about transistors, there is something called ISC, okay, short circuit current, ISC, okay. So that is what it's referring to. Internal current limiting circuit. Okay, so we were talking about the output short circuit current, which I was mentioning, ISC, right? So the internal current limiting circuitry is included in most op-amps to protect the device from damage. Now, this is as good as your stabilizers, right? The stabilizers which actually help, it works as internal current limiting circuitry, okay, which helps in protecting the device from damage, right? So so this can be because of short circuits that can happen. So immediately the stabilizer will have a fuse inside, okay, and because of that, this fuse will be blown off, and due to that, the short circuit at the output is nullified. Okay, okay. So this this stabilizers, they play a very important role, in having this damage control, okay, damage control at the output side. So if you're connecting this to probably a television or an electronic device, then the output that comes from a stabilizer is a stable output. So here we are looking at stabilizing the outputs, right? So if the outputs are stable, then your devices are going to be safe. If, say for example, I have a lot of spikes, okay, in the outputs from from the supply, and I connect it directly to my electronic device, okay, as you all know, these electronic devices these days are very delicate, right? So you cannot expect them to last long. So we need some kind of current limiting circuitry. Okay, fine. So the 741 output short circuit current is about 25 milliamps. Okay, so the range is about 25 milliamps. So keep this in mind. Okay, probably you know, you will be needing this in your problems. Okay, so this 25 milliamp, again, you can see that, you know, in the electrical properties which I have posted in the previous slides. I will come back to that. I will show you. The maximum output current should always be less than the short circuit current, right? So our current should be as less as possible, which means this short circuit current should not be high. Okay, it should be very less. Okay, so the maximum output current should always be less than the short circuit current for satisfactory operation. So only if it's less, you know, then we can say that, you know, there is current limiting circuitry. If not, then there's no point in having a current limiting circuitry. A larger output current is required. Say, for example, I need a very huge current at the output side. Then we can make you know, the use of power transistors. Okay, so these transistors can be operated at higher temperatures, can be operated at higher voltages, can, you know, look after, you know, huge voltages also. Okay, so this power transistors can be connected at the output if in case the reason you know, is that we need higher currents. But if in case we don't need a higher currents, then anyway we are using this internal current limiting circuitry, which will anyway make, you know, the currents as less as possible. Okay, fine. Now I will show you this. Yeah, so this is the 25 milliamps that I was talking to you about, you know, the short circuit current. Okay, so typically it's about 25 milliamps, right? So I hope you have understood what is input impedance, what is output impedance. And again, in input impedance, we have two types, you know, the one with the inverting configuration and the one with non-inverting configuration. The formula changes for the non-inverting type of configuration and for the inverting type. So, you know, these values are to be known in order to solve the problems. Okay, and we have seen that input impedance is fairly large and the output impedance is almost negligible, right? So these are in turn relating to the properties of an op-amp. Okay, so we have seen input and output impedances, right? And we have also solved problems exclusively on input impedance and output impedance, right? So students, any doubts up till this point that we have discussed so far?
No, sir.
Okay, fine. So just make sure that, you know, you go through my notes so that it becomes easy for you to understand, you know, whatever I have taught so far, and do not, you know, keep it for the next day. Okay, as much as possible, try to revise it every day so that, you know, these formulas, how to apply them, and you know, how to make use of these formulas. There are, you know, I've seen instances where, you know, students tend to get confused with the type of formulas, right? With the inverting and non-inverting configuration. Okay, so you have to be careful in looking at the circuit, okay, which has plus and minus terminals, right? So just because of these terminals, you may tend to use another formula. Okay, so because of the other formula, ultimately your answer or whatever time that you have spent in solving the problem goes wrong. Okay, so attention to detail is very much needed when you're looking at the circuit, and try to analyze what kind of formula you're going to use. And you know, most of the time you will get data from the question itself. Okay, you can see that, you know, it says input impedance, voltage follower. These are all keywords. Okay, these are all keywords where you can understand that, you know, it is required to find you know, Zi, and it is required to find in the non-inverting configuration, right? So ultimately your formula will be applied and you can just fill in the blanks, you know, if you have this data with you. I will probably try to provide data sheet, okay, during examinations. We will see how it goes. If not, then probably I will include, these values in the question. So that should be fair enough, isn't it?
Yes, sir.
Yeah, fine then. So I think we'll end our lecture today, and we will continue and look at slew rate and frequency limitations in our upcoming classes. We will see how is the impact with slew rate and what are the limitations with respect to frequency. We will see a few graphs and we will try to solve some simple problems and understand its implications. Fine?
Okay, sir.
Yeah. Okay.
Attendance. Sir, attendance.